Thank you, everyone. Can you hear me okay at the back? Is that enough? Brilliant, thank you. What a great turnout, and thanks for coming along. Hopefully this is interesting. It's an interesting one for me, for sure. And I'll try and... does anybody work in the semiconductor industry by chance? So that's good, because I've got a bit of background, and if you've never seen a chip before, you might learn something, you might not, but let's see. So just about me, so I work for IOActive, of course. I'm the Senior Director of Silicon Lab Services. That is in Seattle, so I travel there quite regularly, but for the last 20 years I've been either analyzing, hacking, or pen testing chips for various companies, and I've been at IOActive for 2 years now. Here is the disclaimer, the legal stuff, which I'm sure you'll read to the word, but I won't hang on that for too long, but it's there anyway. It's just a bit of background as to the kind of component level testing that we do at IOActive. We're going to talk about the fully invasive side of things on the right there, which is really, it's the lowest level you can go to. It's transistor level on the silicon. On the left-hand side, we have non-invasive techniques such as glitching, electromagnetic fault injection, electrical fault injection, all kind of side channel attacks. So we do this in Madrid. We have a lab there, and we have a bunch of experts who are all over this. Then kind of in between, there's a semi-invasive selection of attacks that we try and kind of emulate to inform people that are making chips. So this is, oh no. So the semi-invasive involves, getting access to the die inside the chip package, but not invading it. We just need access to that die so we can get a laser in there and do laser fault injection, things like this. So this is in development at IOActive at the moment. So that's quite exciting. And that will most likely be installed in Madrid. So I think probably everybody knows I have a northern accent, by the way. So if you don't understand anything, just ask. Yeah, we have I think it was released very end of last year, and it's the heart of the Pico 2 of the Raspberry Pi. So what do we know about it? We know it's got a dual core, it has some boot ROM, as almost all chips do. I've highlighted that OTP because that's what we're going to talk about. That's the fuse array, which we'll find out a lot more about. We have SRAM. I mean, as I was saying before, chip you can really describe as a miniaturized computer. So it does have a CPU, it has all kinds of memories and inputs, outputs, and all the things you'd expect on a PC. So why did we want to attack this chip? Because it was interesting, because it was implemented, or was released on a product which was the badge of DEF CON 32. IOActive sent a lot of people there. It runs the same time as Black Hat, I believe, in Vegas. So we had a few of these because we had a few people attending, and the Raspberry Pi was on that. And also it was interesting because it was a challenge that was raised by Raspberry Pi themselves. So it was a big bug bounty campaign that basically challenged people to hack the chip, which is good for them because they get a lot of value out of that for hopefully a small amount of cash. And of course, IOActive, we all like to break things, we like to hack things. That's what we do. We do it at all levels of technology. So the challenge was to extract some key material that Raspberry Pi would implant into the chip in a OTP memory. So it's quite a broad term, one-time programmable. It could be a sector of flash, for example. It could be fuse, it could be anti-fuse. It could even be, it's even been implemented in ROM, which is not technically correct, but it does happen. And this is quite common with data sheets to chips. It can be quite ambiguous. And it's really like, who's going to find out what is true and what's not? They put things on the data sheet and it's not necessarily even present in the chip, but who's gonna prove you wrong? But we try and do that. So yeah, there's no flash in the chip. We know that as much because it says that in the data sheet. So it has to be a fuse or an anti-fuse. Difference between a fuse and an anti-fuse is a fuse starts out as a 1. You can imagine like a wire. When you burn that wire, it becomes a 0. With anti-fuse, it's the other way around. So we start off as a 0. There's no connection, and then something is burned to change the material in the fuse, and that makes it a 1. Kind of makes the transistor work rather than not working. So 1 versus 0. So we had to do a bit of research. You know, what clues can we find in the chip data sheet from Raspberry Pi to begin with? And it already tells us that it's using an OTP memory which is designed and supplied by Synopsys. Synopsys just design intellectual property for chips, and they license it to people. So that's what Raspberry Pi have done in this case. They've used their product in their chip, and there's a lot of stuff in data sheets, let's say. So then we go onto the Synopsys website and we find out, okay, what could be the specific technology which is being used in this chip? And again, it mentions OTP. It's non-volatile memory, OTP, and it's a 40 nanometer technology fabbed by TSMC, Taiwan Semiconductor Manufacturing Company. So we know that our chip is 40 nanometer as well, so it's highly likely it's going to be this or very, very close to this specific technology. It even gives us a nice cross-section of what this fuse or anti-fuse cell would look like, which will be interesting later on. So as I said, you start off with basically a 0, and then when it's written, you supply a high kind of current to this area, and you make a 1 from it. So that a fuse or an anti-fuse is a good way to write data into a chip after it's been fabbed. So it's very cheap, and it's some way of putting a unique identifier into that actual chip. You couldn't do that really any other way. You could do it in Flash, but it doesn't have a Flash. You can't do it in ROM because ROM is a mask. You'd have to make a new mask for every chip, and nobody's going to do that. That would be ridiculous. Fuse is just a good way to put a unique ID on an actual device itself. So a lot more things that we found out on the Synopsys website, but the most interesting thing at the bottom is to say that the state of the memory is impossible to detect using physical attack or reverse engineering techniques. So we thought, okay, let's have a look at this and see if they're telling little, if they're being optimistic or how much do they know. So we had 2 options. One would be fairly easy. This first option is to get past the secure boot, and then you could read out whatever you want from the chip. All right. So the boot ROM is public. We got that. We looked at it, but to the angle of performing a fault injection campaign on it. And if you can get past that secure boot, obviously you can just leak everything you want. You can read that secret data. You can do anything you want. But we didn't find any vulnerabilities in the boot ROM, nothing obvious. There's a lot of things protecting the chip from side channel attacks. The lab in Madrid is too busy, so we didn't have the time to really devote to that. It could be 4-6 weeks of work to find a vulnerability using non-invasive techniques, side channel, glitching, all of this. So what if we could, a fuse is a physical thing, so could we not just read the value directly from the fuses themselves? So first we've got to decapsulate the chip. We take the chip out of the package. Can we find the fuses? And can we find a way to physically extract 1s and 0s from this memory array? So this is what we do in Seattle a lot of the time. So we start off with the packaged chip on the left. In the middle is a beaker of nitric acid. This dissolves the epoxy package and everything else that's inside that package, but it does not damage the die. And that's what we end up with on the right-hand side. That is just a decapsulated, clean die, and that is the Raspberry Pi chip itself. So that's how we start. Next thing we do is take some nice optical images, see what we can find there. All it's got on is, date, RP4, and a nice Raspberry Pi logo on there, which is quite rare these days. So just a bit of background about semiconductor devices, just to try and explain what it is that we're actually looking at here. So I mentioned that's a decapsulated chip, which it is. Essentially that is a fully processed chip, and that would still work if it was connected to the outside world. You can see these little circles around the perimeter of the die, and that's where the wires, the bond wires, would have been, but we've taken them off. So there is that chip is untouched, undamaged, would still work. So it has all these layers of circuitry built on top of each other. But we don't learn a lot from that image because there's not really a lot to see apart from a logo and a date. So the first thing we do is we remove all of that circuitry, all 8 layers of it, and we end up with the image on the right, and that is the floor plan of the silicon substrate. So it's interesting to imagine that all we see on the right-hand side is silicon. There's nothing else on there. The different colors come from the patterns that are etched into in 3D into the silicon, so it reflects wavelengths of light differently. So even at a low level, high level like this, you can kind of identify what is what. These huge blocks, these can you see my cursor there? Yeah, these big blocks, they have to be RAM because there's no other memory that would be that prevalent on the chip. But anyway, we take this optical image, or we take this chip that we've taken an optical image of, and we will put it into the SEM, and then we'll try and identify all of these memory types, and then hopefully we can find out where the fuses are. So a little bit more background. If we sliced open that fully decapsulated chip, fully processed chip, this is kind of what a chip looks like in cross-section. It's like a layer cake. You have 8 layers of circuitry, and it's embedded in an insulator material. So everything in that sort of central image there, anything that's bright white, it's conductive, it's copper. And everything that is around it, the darker material, this is just an insulator. So really you can imagine it as almost like a multi-layer PCB. But the difference is that with a chip at the very bottom, near the substrate, it has actual functionality. A PCB is just kind of it's just transport, really. A chip is the transport, and at the base level, it has the functionality. So it has transistors configured as CPU, logic, memory, and fuses, and all these things. So it's really an integrated device. So we have all these different areas of memory. Probably wondering what this kind of messy area is, and it's not just garbage. It's not a stain. It's not just messy stuff. It's actually the CPU core logic there. So that's where the actual functionality is being implemented. And we've kind of annotated all these different memories with different colors, so we can kind of just tell you which types are which, or differentiate them from each one. I'll just quickly go through them to tell you what they are. So the big one, the main one, like I said, that is RAM. Specific type of RAM, but it's required for all the kind of on the run, on the fly memory. So yeah, there's an awful lot of that memory, but we're not interested in that. Secondly, we have this little purple area at the top. This is another type of RAM. Okay, not interesting. So the image on the right is a scanning electron microscope image of the substrate, just close up. And each memory has a different kind of floor plan, so you can characterize it. This is classic. It looks like SRAM. Without doing too much research, you can just by the appearance of it, it's kind of got this kind of yin-yang kind of structure, and it looks like all RAM memories have this kind of signature. Down at the bottom, the red one, this is a ROM. It's kind of easy to recognize as well. We're not interested in that. We could extract that ROM, but we have the ROM anyway. It's the boot ROM is public, so we don't need to extract that. We know there's going to be nothing interesting. And then we're left with the more interesting one, let's say. So we take a look at this. We can kind of zoom in a little bit more. We've got columns of these, what looks like a memory array. And then we do some nice tilted images in the SEM to give us like a 3D view. And here we get quite interesting. So the structures that are raised, this is where the transistors are based. Anything in the trenches, it's not important, it's not functional. The trenches are for isolation between transistors to reduce the amount of crosstalk between transistors. They fill that with the insulator material just to basically isolate them from each other. So if we look on the right, we start to see things that look a bit like our cross-section from the Synopsys website. We don't have enough resolution there to really see everything, but you can see this hump is one of these humps on the left, and it kind of looks like this area here. And then this big lump on the top is the polysilicon, which is sitting on top. Okay, and then we've done some deprocessing so we can kind of get a decent view of what's going on at all the different levels, all different relevant levels on the way up. And this is what we just rendered out just to kind of demonstrate how things work roughly, what materials are involved. And there's a lot more work than this, but I won't bore you with all of it because it's very complicated and I don't understand a lot of it. So I'm not going to try to, not going to pretend. But really this is, yeah, kind of what they use when they're designing chips and designing memory structures. So how can we get the data out? So there's a technique called passive voltage contrast, PVC. That's what we're going to try. So in short, interaction of a charged particle beam with structures of different conductivity in a circuit. We're talking about charged particles either being electron beams, as in a scanning electron microscope, or an ion beam, as in a focused ion beam. So we have in Seattle both of these things combined into one system. So it's we call it a dual beam, a cross beam, FIB-SEM, lots of different names for it, but that's what it looks like there. It involves SEM for imaging primarily. You can also deposit materials with the SEM beam, but also a very important part of it is the focused ion beam, which allows you to make incisions in a sample in any material. And the FIB with chemicals can also allow you to deposit conductive material and insulator material. So you can imagine it's quite interesting for a lot of things. You can change the circuit if you want to. If you understand the circuit enough, you can look at it, understand it, and then you can make a little change to it to make it do something it wasn't designed to do. But we're not going to use all those techniques for this. So PVC in general, when you get a PVC effect in SEM, it makes insulator material appear brighter than conductive material because the electrons have nowhere to go. They're just sitting on, if you image a piece of glass, you're just going to get electrons sitting on the surface because it can't dissipate. They can't go to ground, so you end up with a really nasty image. In FIB, however, it's kind of the opposite. If everything would look the same, whichever material you're looking at, it kind of looks the same. But if you have a conductor and it's grounded, then it lights up really like a light bulb. And we use this for a lot of different purposes. So when we're doing a circuit edit, for example, we can make sure that we are connected to something which is grounded, or alternatively, make sure we've disconnected something from being grounded. So the line of conductive material will just simply go dark and it will appear like everything else. If it's well connected to something grounded, it will be bright white, very noticeable. So we need to get down to the fuses or near the fuses to try and play around with this technique. So what we do is we use something that looks a bit Dickensian there, but it's a polishing wheel. And it's a quick and easy way to deprocess chips if you have some skills. And it's not easy, I can tell you. But if you've got some time and some motivation with something like that, I mean, that's like $25,000 instrument there. So I'm not like playing it. It's not, you could get something a lot cheaper and you can take a little hand jig like that, which what I'm holding there, and you can get some great results. So I've become a bit of an expert in that over the years. But I didn't prepare these samples. I'm not going to claim for something that I didn't do. So we try in the SEM first. Do we get any kind of PVC effect in the SEM? I think we could have played around a little bit longer. But in the SEM, PVC effects are very, very subtle. Not usually black and white. Here you just see a lot of different shades of grey. And the white dots are contacts. They're tungsten. And the kind of fat lines that are running horizontally, they're polysilicon, I believe. So you get a difference in material contrast with the SEM. more than passive voltage contrast. So it's not that useful. We could have ones, essentially these dots in the two columns there, they are bits. So if we could see an effect, we'd see a darkness, a difference in brightness between bits. Okay, so now we're going to try the fib. We have to be careful with the fib because the fib actually destroys the sample as you look at it. So you have to be very careful. But the good thing about the fib is that you can select a very, very low beam current or a very high one, depending on what you want to do. If you want to dig out a massive amount of material, like, okay, not massive amount of material, but 50 microns of material, then you'd use a very, very high beam current up to 20-something nanoamps. So that's high for fib. If you want to do something very gently, you just want to image, but you don't want to destroy anything, and use a very, very low current. And we can get down to about, on our system, about 10 picoamps. So that's very, very low. You're going to get a good image, and you're not going to destroy anything. So we tried it, and look at what we got. So the same sample, and we can see just about on that line that's highlighted there are some differences between ones and zeros. So everything that's a 1 there has been fused. Everything that's bright there, the bright dots, and the dark ones are 1s, if that's the right way around. So, okay, so we know we can extract 1s and zeros. That's interesting, but how are we going to find the secret? So we don't know that until we fully reverse engineer the addressing circuitry, and we work out exactly how things are programmed into that memory. So really, there was a lot of work involved in that. Every layer of the circuit had to be reversed and kind of annotated, and really have to understand how things are addressed. I'm not going to go through that because it would take all day, and I didn't do it. So I thought, okay, we got to a point. It's like, okay, we understand everything. We can actually write our own pattern into the chip itself. We can fuse a pattern into the chip, and then we can put it in the fib, and we can see what we've done. We see how we've programmed it. So there we go. If you squint a little bit, there's an IOA there. Can you see that? Just about. So, and this is a cat face apparently, right? So people get carried away. Like Andrew Sonnenberg is the man who did a lot of this work. And he got quite carried away. He very much enjoyed himself, along with some other consultants that we have. So here we are. Here is a whole column of the fuse array. So it's like 1/24th, I think, of it in total. And you can see in the sort of center right, we see the IOA, and then we've got the cat face. And then on the left, we've got an arrow. And bingo, that is the address that Raspberry Pi said they were going to put that value in, and we can say, okay, well, we know where that value is now, and there's a big arrow pointing towards it. So if you want to send us a chip with your secret in it, we're going to find it, right? We thought it was like rubbing salt into the wound, but again, we get carried away. So they said, okay, don't worry about it. We're not going to bother sending you with this special chip with a special secret on it because you can clearly get it out. We trust you, so there's no point wasting your time. So that was pretty much the end of the... So we worked with Raspberry Pi. We gave them some time to think about what they can do about it. But what can you do about it? Not that much if you're going to use anti-fuse technology, because passive voltage contrast is a real thing. You can't make it not happen. If you've got a circuit which is conducting, a transistor which is functioning, you're going to get a passive voltage contrast effect. If a transistor is not functioning, you're going to get a different effect. So you can just physically see 1s and 0s like we've shown today. What could you do? You could encrypt that fuse data. So yeah, why not? Encrypt it with a key, which would be embedded in the core CPU. There's a lot of CPU there. You could disperse this hardwired encryption key into the sea of logic. And if somebody wanted to reverse engineer that, they're going to be on a long time, right? It's going to be a very expensive gig to do that. So in conclusion, until we did this, nobody realized that was possible. I'd never even thought about it, to be honest with you. You can image a ROM very easily. You can deprocess and image a ROM and extract that because the physical structure printed into the metal of the chip. So that's obvious that you're going to get that. It's there. You can't hide it. There's PVC is used in a lot of different techniques to extract information, but we never thought about it in relation to fuses or anti-fuses. At that time, when we did this work, we were scoping a project for a client, and it was kind of loosely based around this. So we started to think about it anyway. Then somebody in Madrid noticed that there was a bug bounty on the Raspberry Pi. So it was like, could we do this? Yeah, why not? We're kind of in that thought process anyway. Let's devote a couple of days to it. And yeah, this is what we got. So yeah, basically encrypting, obfuscation, which is very common as well, hiding it somewhere, making it look like something it isn't, can raise the bar, but essentially, fuses, anti-fuses are always going to be extractable by destructive techniques like this. So just to mention the people that did almost all of the work, not me. Andrew Sonnenberg was the project lead. He did he did a lot of it. I'd say on average, I think he did about 70% of the work. This guy's an absolute, literally a genius. We worked together to kind of direct the work. Daniel Sloan did the magic polishing, which was required, because if you can't polish down to that layer, then we got nothing. So that was a very important part of the process. He also decapsulated the chips to do that. Lane, she did all those nice 3D renders. She did the scripting for programming the fuses, etc. And I did a little bit while I was there in Seattle. I did a few of the images, and definitely the best ones. The tilted ones, they were the best ones. So that felt like it flew by within a few minutes, but I'm sure it was longer than I expected. Does anybody have any questions?